Hello students, in the previous video we discussed about transform analysis of LTI system and we solved some example. In that discussion we came to know that how the system can be expressed as a transfer function in terms of Z transform and how we can find the impulse response of the system. Okay. Now in this video we'll be discussing about the two properties, stability and causality. Since the system is LTI system, so it already possesses linear and time invariant property. So we are checking or we are verifying whether the given system is stable or causal. Now to call a system to be stable or causal in Z transform, we make use of the pole zero pattern and the region of convergence of the transfer function. So the stability and causality can be determined from the location of poles and 0. Usually the location of poles is sufficient and the ROC of the transfer function. Now if the system is said to be causal, you can see this, you go through the sentence. If the system is said to be, that is LTI system is said to be causal, its impulse response must be 0 for n less than 0. That means for negative values of n, h of n should be 0. And the second thing is the region of convergence of h of z, it should be outside the outermost pole. So that means you will be having h of z, you find the location of the pole and then the ROC should be outside that outermost pole. That means if you have more than one poles, we have two poles at two different location, and the ROC, if the ROC is outside the outermost pole, then only the system is said to be causal. Now, the second thing, for the system to be stable, this impulse response must be absolutely summable. So this point we already know. And next thing, in with respect to Z transform, the system is said to be causal if the poles of h of z lies inside the unit circle. That means not one pole, all the poles of h of z should lie inside the unit circle in the z plane. So unit circle will have the radius of 1. So all the poles should lie within that, on or inside the unit circle. So then is said to be stable. Now, if you want to call a system to be both causal and stable, it has to satisfy two conditions. So, first condition is ROC must include a unit circle and it must be outside the outermost pole. So, that is the first thing. And next one, all poles must lie inside the unit circle in the Z plane. So, two things has to be verified, or two things has to be satisfied if we want to call a system to be both causal and stable. Okay. So first thing is ROC must include unit circle and it must be outside the outermost pole. And second one, all poles must lie inside the unit circle. So first condition is for causality and second one is for stability. So now based on these parameters, let's find out whether the given system is causal or unstable. Here is an example given. Determine whether the system described below is causal and stable. Now, what is the system they are given? H of z is equal to 2z plus 1 divided by z square plus z minus 5 by, I think it's 16, 5 by 16. Now, in the denominator, we have to find the factors for these two, and we have to rearrange that so that we can uh, express this. If you know express this, we have to find the poles and zeros. In the numerator, we have 2z plus 1, and the denominator, we have, if we take the factors, it will be z plus 5 by 4, another will be z minus 1 by 4. So this two things, the denominator, we found the factors so that the denominator of h of z or transfer function will give the location of poles, and the numerator will give the location of zeros. So we are mainly concentrating on the pole here. So based on that, the location of poles just equate to 0. So that gives you z is equal to minus 5 by 4. Another one is z minus 1 by 4 is equal to 0. So z is equal to 1 by 4. Now if you observe, this minus 1 by 4 is nothing but minus 1.25 to be precise. Another one, this is 0.25. Now if I try to express this in the z plane, so consider we have this unit circle. Now one pole is at location 1 by 4, that is 0.25, which we can say here one pole is there. Another pole is minus 1.25, so this is minus 1, and minus 1.25 lies somewhere here. So this is 0.25. Now if you observe this, one pole exits outside the circle, and that means if the if all poles are not inside the circle, so it is not a stable system. And coming to the causality part, now the ROC must be outside the outermost pole, but here we have to check whether the system is causal and stable. Now the condition says if one condition is not satisfied, then the system is not a causal and stable system. So that means if you observe, from the location of poles, so one pole is outside the unit circle and one pole is inside the circle. So all the poles should lie inside the unit circle, then only it is said to be uh, stable. So that property is not satisfied. So that means it is not both causal and stable. So since one pole is lying outside the unit circle, so I can mention that is z is equal to minus 5 by 4, comma, this system or the system is not both stable and causal. Okay. If you have to check separately, then you have to check the individual properties. But here we have it is mentioned that check whether the system is causal and stable means it should be both causal and stable. Okay, so that's what you have to verify. Now second one, the same thing, check whether the system is causal or stable given the transfer function h of z is equal to 1 plus 2 z inverse divided by 1 plus 14 by 8 z inverse plus 49 by 64 z power minus 2. Now for this, you will get the factors. Now observe this, the powers are in negative, so multiply both numerator and denominator by z square. So if you do that, we will get h of z is equal to z square plus 2z divided by z square plus 14 by 8 z plus 49 by 64. So this I did it only to uh, bring it will be easier to find the location of poles and zeros. Now if you find the factor of denominator, you will get z plus 7 by 8 and z plus 7 by 8, and here you can take z common, you will get z into z plus 2, and this can be written as z into z plus 2 divided by z plus 7 by 8 whole square. Okay. Now finding the location for poles, we have two poles at z plus 7 by 8 is equal to 0. So that is z is equal to minus 7 by 8. So if you take this one, you will get it will be 7 by 8 means point 0.66, I guess. So that is the location here, minus 0.66. So 7, right? I think minus 0.88. 0.8 or something, because you take this 0.70 and it's a 64, and again you get 687, 0.87 something you will get. Now we have two poles which are located at this location, z is equal to minus 7 by 8 or minus 0.87. We have two poles there, and if you look at this diagram, this is a circle, and somewhere here is 0.87, that is the location of pole, two poles. So that means we have two poles, both are located inside the unit circle. So that means uh, the system is stable. And coming to whether it is causal or not, it says that it must include a unit circle. Based on the given system parameters, we can say that we have a unit circle, obviously. So we can conclude that since the location of both poles at z is equal to minus 7 by 8 lie inside the unit circle, so therefore the system is both causal and stable. Okay, so the system is both causal and stable if the poles are lying inside the circle. Okay, now we'll take one more example here. So given h of z is equal to 3 minus 4z inverse 1 minus 3.5 z inverse plus 1.5 z power minus 2. Now for this, the problem is given, specify ROC of h of z and determine h of n for the following conditions. The first condition is system is stable. Second one is system is causal. Now in this problem, first thing is we have to specify h of z, the ROC of h of z, and next is we have to determine h of n for two different conditions. That means while applying inverse transform, we should consider that what if when the what happens what h whatever will be the impulse response of the system if the system is stable, and second what if the system is causal, how then the impulse response of the system will be what. So that's on that basis you have to figure out the impulse response of the system. Okay, now first we have to find the transfer function h of z, and since we have to find the impulse response, we have to apply the partial fraction expansion method for this one. So given h of z is equal to 3 minus 4 z inverse divided by 1 minus 3.5 z inverse plus 1.5 z power minus 2, and this can be written as 1 minus 3.5 can be written as, if you take the factors 3.5, so if you take the factors for this, it will be 1 by 2 z inverse and another will be 1 minus 3 z inverse. So these two are the factors for that. Now using partial fraction expansion method, so h of z is equal to k1 1 minus 1 by 2 z inverse plus k2 1 minus 3 z inverse. So k1 is equal to 1 minus 1 by 2. So I'll be directly writing h of z here. H of z is 3 minus 4 z inverse 1 minus 1 by 2 z inverse 1 minus 3 z inverse, where z takes the value 1 by 2. This to get cancelled. So 3 minus 4 z inverse 1 minus 3 z inverse, z takes the value 1 by 2. If you simplify this, 3 minus 4 into 2 divided by 1 minus 3 into 2, so that is 3 minus 8 divided by 1 minus 6. So minus 5 by minus 5, that is equal to 1. So K2 is equal to 1 minus 3z inverse into 3 minus 4z inverse divided by 1 minus 1 by 2 z inverse 1 minus 3z inverse, where z take the value 3 here. Now this to get cancelled. 3 minus 4z inverse 1 minus 1 by 2 z inverse 3 minus 4 into 1 by 3 divided by 1 minus 1 by 2 into 1 by 3. So this is 3 minus 4 by 3, and here this is 1 minus 1 by 6. So if we take this simplified, 9 minus 4, denominator 6, 6 minus 1, 5 by 3, and here it is 5 by 6, cancels, 2 so 2 goes to numerator. So K2 is equal to 2 here. So therefore H of Z is equal to 1 divided by 1 minus 1 by 2 Z inverse plus 2 divided by 1 minus 3 Z inverse. Now if you look at the poles, so 1 minus 1 by 2 Z inverse is equal to 0. So that gives you Z is equal to 1 by 2, and 1 minus 3Z in is equal to 0. That is Z is equal to 3 you will get. These are the locations of poles, that is Z is equal to 1 by 2 and Z is equal to 3. Now first one, we have to find H of Z. So taking inverse Z transform, so the first condition for a system to be stable, so its ROC must include the unit circle, okay. So therefore we have two different circles, one at radius 1 by 2, another at radius 1 by 3. Looking at this 1 by 2 and 3, another radius 3, 2. Now the ROC we should lie between this. So therefore ROC should include unit circle. So Z should lie between this 1 by 2 and 3. So then only, if you imagine, we have a circle of radius 3 and another circle of radius 1 by 2. Now this ROC should have a here, the unit circle will be here. So this, between these two ROC should lie, then only the ROC will include a unit circle. So that's why the ROC should be in between 1 by 2 and 3. So therefore H of n, so the term related to 1 by 2 here is greater than Z, that means it's a positive time sequence, 1 by 2 n into u of n, and the term related to this 1 by 3, that is negative time sequence. So minus 2 into 3 to the power of n u of minus n minus 1. This is negative time sequence and this one is positive time sequence. So that's why the system is becomes stable. Okay. Next thing, for a system to be causal. So here we are mentioning only the ROC for two different things. When the system is stable, what will be the ROC, and when the system is causal, what will be the ROC. For for the system to be causal, ROC should be, so ROC should be outside the outer outermost pole. So this is from the property of the causality and stability. ROC should be outside the outermost pole. Now we have two poles here, one at z is equal to 1 by 2 and z is equal to 3. Comparing these two, z is equal to 3. So this is the outermost pole. So if the ROC is outside this outermost pole, then only the system is causal. So therefore, if ROC is greater than 3, that is outermost pole, then only the system is stable. So therefore, taking inverse Z transform, you get h of n. If ROC is greater than 3, then it is obviously greater than 1 by 2. So both becomes positive time sequence. So therefore, you will get 1 by 2n into u of n plus 2 into 3 to the power of n into u of n. So this is the impulse response if for a system to be causal, and this is the impulse response for the system to be stable based on the properties of stability and causality. So these are some different type of examples you might get to find the stability and causality of a system. So usually they'll ask to mention both the stable and causality property. And I have one more topic that is left over that I will discuss here. So it is just the relationship between the transfer function and the difference equation. So how they are related to each other. So this one topic I'll cover here only. So relationship between transfer function and difference equation. Now if you consider an LTI system for which the input and output satisfy a linear constant coefficient difference equation of the form. So given k is equal to 0 to n a k y of n minus k. So this output k is equal to 0 to m b k x of n minus k. Now taking z transform on both sides. So you'll get the summation same, k is equal to 0 to n a k. So y of n minus k is here. So the z transform of that will be z power minus k into y of z, and summation 0 to m, this will be z power minus k into x of z here. Okay. Now if you take y of z outside the summation, and in the RHS if you take x of z outside, okay, So the transfer function h of z is y of z by x of z. So that is given by summation k is equal to 0 to m b k z power minus k divided by summation k is equal to 0 to n a k z power minus k. That means if you rearrange this, now what does this mean? This means that the transfer function of a system which is described by a linear constant coefficient difference equation is the ratio of the polynomial in Z inverse, and it is referred as a rational transfer function. And in this transfer function, the coefficients of Z power minus k in numerator polynomial is the coefficients associated with x of n minus k, is the coefficients associated with x of n minus k. And the second term says the coefficients of z power minus k in denominator polynomial is the coefficients of y of n minus k. So this is the relationship between the transfer function and the difference equation. Now this is how we represent the difference equation. If you can remember, summation k0 to m bk and summation k0 to n ak, but we are expressing in terms of z transforms, and we are trying to get the relationship between the transfer function and the difference equation. Now if you difference equation is given, say for example something like y of n minus 1 by 2 y of n minus 1 is equal to x of n minus 1 by 2 x of n minus 1, something like this, okay, or 1 by 2 or 1 by 4. We have to apply z transform for that. You will get, and here you will get x of z minus 1 by 4 z inverse into x of z, and you take y of z outside, you will get 1 by 2 z inverse, and if you take x of z common, you will get 1 minus 1 by 4 z inverse. Now if you rearrange this, y of z by x of z is equal to 1 minus 1 by 4 z inverse divided by 1 minus 1 by 2 z inverse. So this is the transfer function of the system, which is expressed in terms of difference equation. And the remaining steps is the same. We have to find if a transfer function is asked, we have to conclude here, or if the impulse response is asked, we have to apply the partial fraction expansion method, and you have to find the impulse response of the uh, transfer function h of z. Okay, I hope this stability and causality property you have understood this, and the relationship between this transfer function difference equation. This is just a topic you should know what is the relationship between transfer function and difference equation. uh, I was supposed to discuss this in the previous video, but I'm discussing this part in this one. Okay, and like this similar examples, try to solve a different number of problems. They're based on stability and causality and transform analysis of LTI system. Hope you understood this method. If you have any queries, do reply or comment on this video. So thank you for your time.